Okay, let's look at a simply supported beam, meaning there will be a pin at one point as well as a roller on the other point with a uniformly distributed load on it. In lecture 6 or in lecture 5? In lecture 5 you learned how to draw the bending moment diagram of this. So we're going to follow the same steps, but with this thing in mind that we want to calculate the deflection of the simply supported beam. Yeah. So as a method, I'll draw two axes. One of them will be length of beam. As you can see is L. The other one is deflection. And I'm sure you all can guess that if such a load, such a uniformly distributed load, for example, an elephant is sleeping on this beam, is applied to this beam with these support conditions, the deformed shape, the deflection, will look something similar to this, very symmetric as well. Do you accept at this point, at a micron in the middle, the slope of this deflection will be zero. Zero slope. Yeah, so at any point, if I have this beam and I just deflect it, as you can see at a point, the slope at a micron, it will be straight. So the slope will be zero, while at any other point, there is a slope, and the slope is changing as well. Yeah, let's have that in mind. On the other side, we just discussed about boundary conditions. If you remember, in case of a pin, we said the deflection is zero at the point of the pin, the micron which the beam connects to the pin support. But there is slope. The same thing applies with the roller as well. Again, we said deflection is zero at that micron which they connect. The deflection, I can either show it with the capital delta or this, and there is slope. I don't know the value, but there is slope, as you can see. It's not against the fixed support, which there wasn't any slope. So far so good. The next step, so we put the axis, we figured out what are the boundary conditions of the supports. The next step is to calculate the moment. So let's calculate moment function. If you remember, we discussed about function, for example, something like this, which you put an x into it and you will have an outcome. For example, this is a function that you put y into it and you'll get you put x into it and you get y. So I can write this like this as well. Y is a function of x, or fx is x to the power of 2, for example. So I want to formulate the moment function of this beam. And we already know it from lecture 5. So let's see what we were doing. So I'll just draw the idealized shape, the free body diagram of it. The pins that I have, the uniformly distributed load that I have on it. It's a W. This is a length of L. If you calculate the reactions, I'm sure you'll end up with, because it's symmetric, by this time you have calculated so many cases that you are much faster. So this is W times L divided by 2. This is W times L divided by 2 because it's symmetric. If not, you can use the equations that we had. Summation of all forces in y in x equals to 0, summation of all forces in y equal to 0, and summation of all moments will be equal to 0. Using these equilibrium equations, you can figure out that this is WL divided by 2, this is WL divided by 2. And this is the actual free body diagram of the entire beam. Now, in order to figure out the moment, we were saying, let's cut it a micron after something happens. It's a distributed load, so nothing is happening here all the way to this support. Yes, so I start from the left side of my beam, I carry on to the right, and I'll just cut a segment. Yeah, I'll cut a section here. I bring that section out, and it will end up something similar to this. It will have the same W. The length is now X because it's a micron before L. And I'll have that WL divided by 2, which is from my reaction. The only thing which is lost is this reaction because I cut it a micron before it. And I was saying that if this is the convergence of the positivity, so moment, and then over here, let's say goes up, shear, and comes down, shear. This was the standard that we were always following. Because I'm cutting on this side and I'm looking at this side, I will draw the same here as well. There will be a function of shear, and there will be a function of moment. Because I cut it internally, these two will be happening into it under this applied load of W. Can I solve this? Yes, easily. We were saying that whenever we see this condition, we can quickly convert that distributed load to a concentrated load. Let's apply a concentrated load, and this will be W times X. Yeah, the equivalent concentrated load of this distributed load. Where does it apply? To the centroid of the distributed load, which we have proven it as well, which will be X divided by 2. Yeah, from both sides, because the length of my new beam is X. Now it will be applied in the middle, so X divided by 2. Let's get a moment along this point. Let's call it O. So summation of moments along point O equals to 0. I'm considering this direction as positive. So how does it end up? This going around O is positive. So WL divided by 2 times X. This arrow with the center of O going around it will be negative. It's against the direction that I considered positive, you see. Is anti-clockwise while my direction is clockwise. So it will be negative Wx times the distance that it has to that point, which is X divided by 2. Yeah. And then I have a moment here, which will be again negative as well. So negative mx equals to 0. I can simplify this and bring m to the other side. So the moment function can end up something similar to this, which I'm sure you all can get to it. Minus wx to the power of 2 divided by 2. This is the moment function. This is from lecture 5. And this is the moment function. Yeah, everyone happy? Similar to this that we were saying, we put x inside it and we get y, or we get function of x. You put x at this point, at any point, and you get the moment value of it. Now let's zoom out. I now have the moment function, perfect. But what was I looking for? I was looking for the deflection. And we said deflection is calculated with such formula. Yeah, we prove it through the elastic beam theory. And we said we put this negative because if we get a positive value of this deflection, we know that the positive value means that deflection is downward. That's why this negative exists over there. This m is the same m. Let's replace it. So now we have deflection equals to negative blah 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 1 over ei times that moment function, which will be wl x divided by 2 minus wx to the power of 2 divided by 2 d of x d of x. Can I solve this? Yes, it's not a sophisticated formula. Let's try to solve it. So the double integration looks something similar to this, yeah? I'm just changing the integration to derivatives. I'm multiplying this negativity in it as well, so minus wx divided by 2 plus wx to the power of 2 divided by 2. Let's get one differentiation less, so we integrate this. So d of v, d of x, these are the simple maths that you have studied so far. 1 over ei is like getting an integration from inside that. So this will be negative wl x to the power of 2. A 2 comes down, times 2 will be 4, plus wx to the power of 3. The 3 comes down, times 2 will be 6, plus a constant that we don't know. Let's get another integration from both sides. We end up with this. You see, double, single, actual. Let's do the integration again. Negative L x to the power of 3. 3 goes down, 12. Plus wx to the power of 4. 4 goes down, 4 times 6, 24. Plus a was a constant, so now we'll have an x, plus a new constant introduced. I have a problem here, I have a problem here. I have equation 1 and I have equation 2. And remember this as well. Isn't this a little bit familiar? Didn't we say theta is the slope? So this is actually the slope. And didn't we say at this point is equal to 0? So if I put this equal to 0, don't I get a value for x? If the whole thing is slope is 0, it will be the maximum position where the deflection has happened. So I can figure out where is the maximum position by just putting the entire thing of this slope to 0, and then I'll get an x. We can guess it from now that it will be at the middle of the point because everything is symmetric, so it will be L divided by 2. But just have it in mind that this is the way to figure out where the maximum deflection happens. We get the equation 1, which is the slope equation. We put instead of slope 0, and then we solve it for x. But let's get back to the question. We have a problem of a and b. How can we solve it? We go back to the boundary conditions. The boundary conditions are saying that at the supports, which one of them is at x equal to 0 and one of them is at x equal to L, I have these conditions. The slope exists, but the deflection is 0, the deflection is 0. Can I use it? Yes. Oops, sorry. So let's find a, constant a, and b using boundary conditions. So simply at x equal to 0, my deflection is 0. So no deflection at pin support. I mean at this point. At x equal to L, my deflection is 0 again, so no deflection at roller support. I mean this point, as we just assumed in the beginning. Let's put these values in this equation that we found, and we can get the A's and B's. So if I put x equal to 0 in equation 2, and I know that the deflection is 0, so this will be 0, all of these x's will be 0. I end up with one b, and trust me, that b will be 0 as well, because the entire thing was 0. So b equals to 0. One constant solve. Let's put x equal to L again in equation 2. I know the entire of this equation, the deflection will be 0. So this is 0. Instead of every x, I put L. So this will be L to the power of 4. This will be L to the power of 4. This will be 0. I have already calculated it. And this will be AL. If I simplify it and solve it, trust me, A will be WL to the power of 3 divided by 24. Remember, if this is 0, this xi multiplied by 0 will be 0 as well. So I'll just end up with such a thing inside this. And if I simplify it, you can already see L to the power of 4, one L over here as well. I'll bring it to the other side. L will be divided. So WL to the power of 3 divided by 24. A done, B done. I can rewrite this equation with this inside it as well. L, I know exactly how much it is, and I can figure out the x. Let's find the deflection at mid-span. Mid-span meaning x equals to L divided by 2. So let's say maximum deflection at mid-span, which in this case, let's say L divided by 2 is the x that I will input. If this is my equation, I can simplify it, so I can put B as 0 and A as the other one. So let's write it down. I'm just putting this instead of here. So deflection will be 1 over EI negative WL x to the power of 3 divided by 12 plus W x to the power of 4 divided by 24. Yes, plus I'm replacing A with this WL to the power of 3 divided by 24x. WL to the power of 3x divided by 24, and B is 0, so I won't put it in, I'll just ignore it. This is the deflection function of that simply supported beam under uniformly distributed load. Now if I put x equal to L divided by 2, meaning mid-span, mid-span, which I know the maximum deflection will happen. If I put L divided by 2 over here, will be L to the power of 3 times L to the power of 4. That 2 to the power of 3 times 12 plus L to the power of 4, 2 to the power of 4 plus all of these will end up 5 WL to the power of 4 divided by 384 EI. I strongly suggest that you do that and see whether I'm right or wrong. Also, positive sign, because if you remember, at one point here I multiplied this negativity in all of these guys, so that's why this became negative, this became positive. So if this formula is positive, the positive sign indicates sign of, let's say, deflection indicates that movement is downward. So the beam is coming down. As simple as this. As long as you figure out what is the moment function and you figure out what are the boundary conditions, you can simply get the function of deflection. Any x that you put in this formula, you'll get the deflection. We put L divided by 2. You can put x equal L divided by 4. Then you'll find what is the deflection here. We calculated what is deflection here. Trust me, if you put x equal to 0 or x equal to L, you'll get 0 deflections. As we discussed, due to the boundary condition as well, deflection here and deflection here will be 0. Deflection at the midspan will be maximum. What is that maximum? That's where this is equal to 0.